Alright, so 1.1, solving simple equations. And today we're actually going to only stick to part of the chapter. Your goal is to understand how to solve one-step equations, but only ones that are involving addition and subtraction. Multiplication and division we're going to tackle on a different day. Alright, and the way we're going to start this off, we're going to start off by looking at a simulated model of balance scales. And you'll see what I mean on the next slide. One common way to think of equations is to visualize them as balance scales, where the equal sign is the center of the balance scale, and then what's on the left of the equation, what's on the right of the equation, those are the weights that go on our balance scale. Now in this case, let's start with the right side. Equal sign is our middle, so 9 means we're going to put 9 weights on the right hand side of this balance scale. And of course, just like you'd expect, our balance scale tilts to the right because there's nothing on the left side yet. So there's 9, 3, 6, 9. Now, on the other side of the equal sign, I've got x plus 3. Well, the 3, that would mean 3 blocks. But then x basically represents some mystery weight. It's a physical weight we can put over here, but we don't know how much it weighs. Now, in this case, it balances things out. Now, the reason why people think of equations as balance scales is because if you use a little logic, we can pretty much get our answer. And we want to basically ask ourselves the question, what can we get rid of from this picture that might make life a little easier? So hopefully what you thought of is that, well, you know what? Since I've got x plus 3 weights on this side, and then I've got 9 weights on this side, what we could do, yet keep the balance scale still level, is to subtract 3 from both sides. So that's what I'm going to do here. I'm going to take away these 3 tiles. And that's going to be okay because as long as I do it to the other side of the balance scale, everything still stays balanced and they still equal each other. So what I'm going to do is I'm going to subtract 3. So notice how 3 tiles disappeared here, 3 tiles disappeared here, and there's my answer. Our mystery weight is equal to 6 tiles, or 6 weights. So x equals 6. Alright, so let's take a look at another example. In this case, one that deals with subtraction. Now, it's going to get a little trickier because of the nature of subtraction, but we're still going to try the same approach. First off, realize that to represent this equation, 6 equals x minus 2. The equal sign is the fulcrum point. It's the middle of the balance scale. So the 6 blocks that I pull out go over here. Then the equal sign. Now x, just like in the last example, represents some block of some mystery weight. And it weighs it down. Now in this case, minus 2 is a little different. If this was plus 2, I'd add 2 more blocks. But basically, minus 2 is saying take away 2 blocks, or take away the effect of 2 blocks. Now, the way we're going to represent this initially is we're going to use balloons. If 1 block weighs something down, then 1 balloon counteracts that weight and pulls upwards. So if I put 2 balloons out here, it's basically counteracting the weight of 2 blocks, and it evens out my balance scale. So something minus 2 is equal to 6. Now, this is where again it gets a little trickier because we don't have balloons on this side to cancel out to make these 2 disappear, but that's what we'd like to have happen. We'd like these 2 balloons to disappear so that I'm just left with x, and that will tell me what x is equal to on the other side. Now, the way we want to think of this is we may not be able to physically get rid of the 2 balloons, but we can get rid of their effect. Their effect is to pull up with a weight of 2. So what we're going to do is to counteract that, we're going to add 2 blocks to both sides. So by adding 2 blocks to this side, the effect of the 2 balloons will cancel out, and then as long as I do it to the other side, I should be fine. So let's click go. So my 2 balloons, the effect of those balloons disappeared, and I counteract the missing balloons. 2 tiles got added over here, and we get our answer. 8 equals x, or x equals 8. So this is the idea that we're going to try to work on today. And this gets at something, the idea that we always want to keep our equations balanced. And you'll see something about that in the next slide. Okay, so we've just finished up with our balance scales, and now we want to sort of formalize this so we understand some of the rules that we're actually applying here. Now, in our balance scale scenario, we're looking at keeping things balanced. What we were really using was the mathematical addition property of equality. And what the property of equality says is that adding the same number to each side of an equation, so let's say our equation is a equals b, there's one side of the balance scale and there's the other, and they're balanced, that adding the same number to each side of the equation produces an equivalent equation. Meaning that if I just choose to add C number of blocks to one side and C number of blocks to the other, it's still balanced and it still represents the equivalent equation to the original. The same thing goes for subtraction. The subtraction property of equality is that when subtracting the same number from each side of an equation produces an equivalent equation. So once again, if I start off with a balanced scale that has A equal to B, then A minus C should still be equal to B minus C. As long as I do something to one side of the equation and I do it to the other side of the equation, everything remains balanced, just like our balanced scales. Alright, so let's see what this looks like in terms of our work. We're going to be doing some work with these one-step equations involving addition and subtraction, and we want to apply the property of equality. Alright, so let's take this property of equality and actually apply it to some equations. So here's what we want to do. X plus 7 equals 18. We're trying to solve for x. And so the clearest way we can see that is that if we can get rid of this plus 7 and get x by itself, on the other side we'll have the answer. And so we're going to use the property of equality to do this. So right here I can get rid of that plus 7 by just doing its opposite, subtracting 7. And this is okay to do as long as what I do to one side of the equation I do to the other side. So on the other side of the equal sign I'm going to also subtract 7. This keeps my equation balanced, and so when these cancel each other out, plus 7 and a minus 7, since they're opposite operations, I just get x, equal sign drops down, and 18 minus 7 is 11. And then we can go back, check our work, stick in 11 for 7, and 11 plus 7 does equal 18. Okay, now here's another way to show that same work. I'm going to take the same problem, but here's a slightly different variation of showing your work for the property of equality. We know we're trying to get the plus 7 to just become 0. We want it to disappear. So what I can do is I'm just going to go ahead and cross that out. And then my next move will be to go to the other side and do its opposite, which is to subtract 7. It's essentially the same mathematics we're doing here. We're just showing it in a different way. So now I've got x equals, and then 18 minus 7 equals 11. And we already checked it, so we know it works. All right, so two different ways to show your work. Let's see that again on a different problem. Here's another one. 21 equals n minus 4. Now this sometimes throws people because this time n, the variable we're solving for, is on the right side. But that doesn't matter. Okay, all we care about is we're trying to get n by itself. So I need to get rid of this minus 4. So once again, one way to show this work is to add 4 to this side. And what I do to one side of the equal sign, I do it to the other. Draw a line. Now over here, we intentionally did this because these are opposites and we'll just cancel each other out. We'll get n, equal sign drops down, and 21 plus 4 is 25. Check our answer. 21 equals 25 minus 4. Plugging our answer back in, and 21 does equal 21. So that checks out. All right, so notice how it didn't matter that n was on the right side. We're just trying to get n by itself and solve for it. It doesn't matter whether n's on the right or n's on the left. Now, if I want to show that the other way, same as before, I know I'm trying to get the minus 4 to become 0, so I just cross it out, and then I do the opposite move on the other side. So plus 4, which is 25, equals n, or n equals 25. Okay, now, here's one I chose because this sometimes trips people up. And the reason why is because of this minus and the negative. And the idea being that what we're trying to do here is the opposite operation. And sometimes people take this opposite piece too far. Okay, so for example, if I go back here the move was plus a positive 7. So we subtracted a positive 7. Notice how we did the opposite operation, but the number itself didn't change. It was positive 7 here, positive 7 here. Same thing on this last problem. We had minus 4, or minus positive 4, and we did plus positive 4. We did the opposite operation, but the 4 stayed positive 4. Okay, so we don't do anything any different here. Here it's g minus this number, so I'm going to do the opposite. I'm going to add that number. So notice how I did the opposite operation, but the number itself, even though it was negative, just stayed negative 4. What I do to one side, I do to the other side of the equal sign, and then I do my work. These cancel out. G drops down, equal sign drops down, 10 plus negative 4 would turn out to be 6. And to check my answer, plug 6 back in. 6 minus negative 4 equals 10. Minus a negative is plus. And 6 plus 4, 10 equals 10. So it checks out. Okay. Now, here's another option for that problem. I'm sure a lot of you saw that from the beginning, we could have maybe made this a little easier, that this minus and negative can get confusing. And so before you actually start solving the problem, we could have done the trick where we do minus a negative is the same thing as plus a positive. Some of you from your previous teacher might have learned it as the keep, change, change trick or the same, change, change trick. But it just means when you have minus and negative, it's the same thing as adding a positive. Okay, so now we get this. And now it's a lot easier to see what our move is here. It's g plus 4. We're going to subtract 4. What I do to one side, I do it to the other. These cancel out. I get g. And 10 minus 4 is 6. Same as what we got here, just done a little bit differently. So mainly here, just be careful with the negatives and the positives and the pluses and the minuses. And just realize that what we're doing here is the opposite of the operation, but not the opposite of the number.